Okay, so we have finished with all the new material for the class. All that remains is to go over the key to get a little bit of practice for the final. So the key for the practice final, that is. So let's start doing that. The first problem on the practice final is this one, which is a more or less standard calculate things around a cycle kind of problem. So the problem is that I have this PV diagram. I have three different states on the diagram, all equilibrium states. I have a reversible process that can take us all the way around from the cycle, from state number 1 through states 2 and 3, and finally to state number 1 again. And we want to calculate all these quantities: the work, the heat, the energy, enthalpy, entropy, and Gibbs free energy for going around a full cycle. So let's do that. The hard ones are the energy and the work and the heat. And so let's go through those. First of all, I'm going to just draw a picture over here, I think, to make things a little easier. Here's our cycle. This is 1, 2, and 3. And this is 30 atmospheres, this is 10 atmospheres, this is 1 liter, and that is 3 liters. So there's a delta P here of 0 and a delta V of 2 liters. On this step, there is a delta P of 20 atmospheres, minus 20 atmospheres, and a delta V of 0. And this step is isothermal, so it has a delta T of 0. So we want work is going to be equal, let's call this A, this B, and this C. So work is going to be WA plus WB plus WC. WA, it's an isobaric process, so constant pressure process, so minus P times delta V. That's equal to minus 30 atmospheres times a delta V of 2 liters for minus 60 liter atmospheres. And for the moment, those are inconvenient units, but for the moment I'm going to leave it in liter atmosphere units. And if you've looked at the key, you can see why. It's just convenient to use liter atmospheres for this problem. For the work for number B, there is 0, right, because there is no volume change. Anytime there's no volume change, there's also no PV work anyway. And WC, that's an isothermal process. It's an ideal gas. So minus nRT log of, in this case, this is V3 and this is V1. The final is V1 and the initial is V3, so V1 over V3. nRT in this case, using the ideal gas law, is just P1V1 or P2V2. If you do either, P3V3. If you do either of those, you'll see that they give the same answer. So, and that's because it's an isothermal process. And so I'll use P1V1. So that's equal to minus P1V1 log of, let's see, V1 is 1 liter over 3 liters for V3. P1 is equal to 30 atmospheres. V1 is equal to 1 liter. So that's equal to minus 30 liter atmospheres log of 1/3. And that turns out to be, looking over on the other page, 32.96 liter atmospheres. So overall, W is equal to the sum of all those, which is minus 60 plus 32.96, which is equal to minus 27.04 liter atmospheres. And now finally I convert that to joules, and it turns out to be minus 2739 joules. So the conversion factor is 101.3 joules per liter atmosphere. All right, that's the work. Let me add a new page here. Now the heat, that's also equal to QA plus QB plus QC with, now first of all, we know that for a state function like all these last guys here, we know all those, the change in all of those going around the cycle's got to be 0. So we know that delta U going around the cycle is going to be 0, and that's got to be equal to W plus Q. So we already know the answer for Q. It's going to be equal to minus W, or in other words, plus 27.04, or plus 2739 joules. And I guess we could leave it at that. In the key, and I guess I won't go through it just for the lack of, just to save some time, but in the key I calculated all these things step by step individually, and you can see that in fact you do get the same answer as minus W, so all of that works. And I guess just to save time, yeah, I won't go through that. All right, so for the rest of these guys, delta U, delta S, delta H, delta G, for any full cycle, whether it's an ideal gas or not, doesn't matter. These are all state functions, and so all those guys have got to be 0 if you return to the same state that you started with, right? The difference between U at state 1 and U at state 1 after you've returned, that difference has to be 0, and so all these quantities have to be 0. All right, that's part A. Part B is to do the same set of calculations, work and heat, and change in U, change in H, change in S, change in G. I think that's all of them. Yeah. But not for the full cycle now, just for the first 2 steps. So from step 1 to step 2, and then finally to step 3. But we already have the number for the full cycle, and so we can, if this is step C here, then we know that, for example, work for steps 1 goes to 2 goes to 3, that's got to be equal to the work for the full cycle minus the work for just part C. And likewise for Q, that's just Q for the cycle minus Q for C. And we know that these two guys are related to each other, right? Q is equal to minus W overall. So that's going to make things easier. And then delta U for 1, 2, 3 has to just be 0, right? That's the U for the cycle, minus U for step C, and so on for all the others. And so on. So I won't go through them all. All right. So all we need then is the work for C, the Q for C, and so on. So let me just list them all out and then I'll calculate them. I guess that's the systematic way to do it. Delta U for C, delta H for C, delta S for C, delta G for C. Those are the quantities we're going to need. So for work, it's again an isothermal process for C. And so it's minus nRT log V1 over V3. That's the work for C. We already calculated that upstairs. It's plus 32.96 liter atmospheres. And so the work then is going to, and I guess I'll just leave that for now. We'll come back and do the work later. Let me make sure I got that number right. Yes, it's plus 32.96. And for the heat, it's going to be equal to just, it's an isothermal process, so heat has to equal minus W, so it's minus 32.96 liter atmospheres. Delta U has to, for step C has to be 0, right? Because it's an isothermal process for an ideal gas. Same for delta H. For delta U is 0 all the way around, but it's also 0 for step C all by itself because it's an isothermal process and this is an ideal gas. For an ideal gas, energy and enthalpy only depend on temperature. Temperature doesn't change, then there's no change in energy or enthalpy. Delta S is equal to the heat change for that step divided by T. Again, it's a constant process, constant T process, And so that would be nRT log V1 over V3 over T, so that's just nR log V1 over V3. The n is equal to 1, and so that is equal to just, let's see how I did that. Yeah, I just did the calculation. That is equal to 0.08206. I did it in liter atmospheres. V log of 1/3. And that is equal to, let's see, over here, it is equal to minus 0.09015. And that's liter atmospheres per degree Kelvin. Delta G is equal to, delta G for C is equal to, let me add another page here. Delta G for C can be calculated in a couple of ways now. Let me give myself some more space down here. First of all, we could use delta H of C minus T delta S of C, right? For an isothermal process, that's true. And we could compute it that way. That's a 0. That makes things easier. So all we'd have to do is take that number and multiply it by T. That would be fine. That would work. But it's also equal to the reversible work. And all these steps are reversible, right? So we already know the number, in fact. It's equal to 32.96. Sorry, 96 joules. And so those are all the numbers for the C step. That means that delta W for 1, 2, 3 is going to be equal to W for the cycle minus WC. That's equal to, well, W for the cycle was minus 60 plus 32.96. Now we're going to subtract 32.96, so it's just equal to minus 60 liter atmospheres. Q123 is just going to equal to minus W123, and that's equal to plus 60 liter atmospheres. U, delta U for 1, 2, 3 has to equal 0, right? Because delta U for C was 0, and delta U for the whole cycle is 0, so delta U for 1, 2, 3 also has to be 0. Delta H for 1, 2, 3 likewise is 0. Delta S for 1, 2, 3 is equal to delta S for the cycle, which is 0, minus delta S for C, and so that is equal to plus 0.9015 liter atmospheres per K. And we can convert that. I think I did convert that over here. Yes, times 101.3 to convert that to joules per K, which is the more usual unit. That's 9.132 joules per K. And then finally delta G, that's just equal to the reversible work for C. And, delta G for 1, 2, 3 is equal to delta G for the cycle, which is 0, minus delta G for C. That's equal to delta G for the cycle. Well, that's just equal to, this is just equal to work for the cycle, right? And so that's equal to minus WC, which is minus, I think, yes, minus 32.96 joules per mole, I guess. And I think that is it. Let me convert these numbers to joules, just to put things in more normal units. This is minus 6078 joules. This is plus 6078 joules. And the delta G down here is minus 3339 joules. All right, so that's number one, all of number one, well, except for part C. Part C says, what's the total surroundings entropy change? And what's the total entropy change for both system and surroundings? And I can't remember whether it asks for those numbers for each step or for the overall cycle, but it doesn't matter because all the steps are reversible. For any reversible step, the delta S for surroundings is equal to minus delta S for the system, which we've already calculated. And the delta S total for any reversible step is always equal to 0. So we already have all the answers for part C. All right, that is all of problem number one. Now let's look at problem number two. Yes, okay, so that was part of problem number one. Problem number two has several parts. The first part is fairly easy. Let me come back over here. It asks which of these quantities is an intensive quantity. So an intensive quantity is either a force, a thermodynamic force, or a ratio between two extensive quantities. Almost all the natural quantities are extensive. So entropy, for example, is extensive. But molar energy is intensive. A force is intensive, a force is intensive, another force is intensive, a molar free energy is intensive, Gibbs free energy is extensive. An extensive quantity divided by an intensive quantity is still extensive. So even though that's a ratio, it's not intensive. But an extensive quantity divided by another extensive quantity is intensive. So that's intensive, and of course moles is extensive. So the intensive quantities are this one, most of them are intensive, in fact. All of those. All right. Then there's a long question, which I think we'll deal with over here, on the contributions to the heat capacity for a pair of molecules that are being compared in every case. So in the first case, it's ethene. So ethene, just to be sure everybody's on the same page, is this, versus ethane, which is the single bonded version of the molecule. And we want to know what contributions, which of these two has the biggest heat capacity at constant pressure, and also what the contributions from each degree of freedom in the molecule is to that heat capacity. So for ethene and ethane first, we're going to do it for that, then there's F2 and Cl2 over here, then there's some others down below. So for ethene and ethane, there's going to be a contribution to the heat capacity from the fact that it's the heat capacity at constant pressure. These are ideal gases, so there's an extra R contribution to CV just from the fact that it's a CP that we're after. But that's the same for both, so that doesn't help us decide which of these two is bigger. Then there's a translational contribution. That's also the same for both, right? 3/2 R for either ethene or ethane, for any molecule, in fact. Then there's a contribution from rotations. They're both nonlinear molecules, and so their contributions from rotations are also identical for the rotations, and both equal to 3/2 R. So all three of these guys don't make any difference between ethene and ethane, and that means that the only thing that can make some difference are the rest of the degrees of freedom. For ethene, there are no internal rotations up here, and that means that it's all going to be vibrations, and there are 12 modes of vibration because there are 6 atoms, and 3 times 6 is 18, minus 6 is 12. For the ethane, on the other hand, there are 8 atoms, so 3 times 8 minus 6 would be 18 modes, but one of the modes has been replaced by this internal rotation. Whenever you have internal rotations, there's one less vibrational normal mode in the list of vibrations. And so it's 3n minus 7 for this case, so 17 normal modes. So there's already more normal modes for ethane than there is for ethane than there is for ethene. And then there's also this extra internal rotation, which will contribute 1/2 R, as we saw in exam 3, to the heat capacity for ethane. More modes and an internal rotation both mean that this contribution should be bigger for ethane than for ethene. And so I say down here, I make a prediction for which one will be bigger. I predict the ethene will be smaller, the ethane will be larger, and because I think this contribution or these differences are going to be reasonably substantial, I say larger and by quite a bit. If we look up the numbers from the tables, it's about 43 for ethene and about 53 for ethane, so ethane is indeed bigger and indeed by a fair margin. All right, that's for the two more complicated cases. Let's look at these simpler molecules now. Again, there's a contribution of R for converting CV into CP. There's always a 3/2 R for the translations. These are both linear molecules, so there's a contribution of R for the rotations as well. And again, none of these things distinguishes F2 from Cl2 so far. Now, there's one mode of vibration for each, right? These are both diatomics, so there's only one mode. F2 is going to be stiffer. Why? Because the molecules are lighter. The atoms are lighter. Cl2 has pretty heavy atoms. And I think the bond is a little stronger for F2 as well. So, I mean, I'm not sure about that, but I think so. So, there's only one mode each. This one's going to be stiffer. This one's going to be softer. This one should have the bigger contribution. Probably neither contribution is very big, but of the two, the Cl contribution from the modes will be larger, sorry. And so I predict that F2 will have the smaller heat capacity, Cl2 will have the larger heat capacity, but it won't be a very much larger heat capacity. And if we look it up, it's 31.3 for F2, 33.9 or about 34 for Cl2, so indeed that prediction and the fact that it's not a very big difference are both correct. All right, the next pair is for water and for ethyl alcohol. Now, just looking at those two molecules, this is a much bigger molecule. You gotta believe the heat capacity, the molar heat capacity for that much bigger molecule is going to be bigger. So even before we go through all this list, I make the prediction down here that the ethanol is going to be larger, and it's going to be quite a bit larger. And looking at the numbers, indeed that's true, 34 more or less for water and 66 for ethanol. And that's because, of course, ethanol is just a much bigger molecule. That's what you'd always expect. But let's go through the contributions. All three of the top ones, the CP contribution, the translational contribution, the rotational contribution, are the same for the two because they're both nonlinear molecules. The vibrations, there's a lot more vibrations for the ethanol just because there's a lot more atoms. And there's two internal rotations for ethanol, right? There's one, let's see, where can I draw this? Let's draw it down here. Here's ethanol. Here's the hydrogens. And then there's an OH2. There's a single bond rotation here, and there's a single bond rotation here. Both of those are internal rotations. And so there's more modes, and there's two internal rotations. Both of those are going to contribute, especially the internal rotations are going to contribute quite a bit to the heat capacity of ethanol. And so those are the differences. Those are the reason for the relatively large heat capacity for ethanol. I guess I'd make a comment here. Notice that I didn't say, I mean, these are all single bonds too. Why didn't I say those were internal rotations? Well, if you're trying to rotate a single atom at one end like this, it doesn't have any moment of inertia. So it doesn't, I guess strictly speaking, it is a rotation, but it's a rotation with no moment of inertia, so it doesn't contribute. It's the modes, it's the vibrations that contribute when it's a single atom like that hanging out on the end. All right, last case, and in some ways most complicated case a little bit. The comparison is a little harder in this case. We're comparing the heat capacity for a solid to the heat capacity for a gas. And so because they're not so similar anymore, they're not two gas phase molecules, it's a little bit more complicated. For the silver solid, first of all, the heat capacity, this is not an ideal gas, so the heat capacity at constant pressure is essentially the same as the heat capacity at constant volume, and so there's no contribution for switching from CV to CP. There's no contribution from translations. This is not a free molecule running around. There's no contributions from rotations. There are no rotations. But there are all those contributions over here on the CO2 side, and when you add all those up, there's already 7/2 are contributions from CO2 over here. On the other hand, using the Einstein crystal model to understand the heat capacity for the silver, there are 3 times Avogadro's number per mole of vibrations for all the silver atoms in a mole's worth of silver crystal. And if we were in the high temperature limit, the vibrational temperature for all those vibrations is at about room temperature, so we probably are not too far from the high temperature limit, in fact. If we were in the high temperature limit, every one of those modes would contribute 1 R. Every Avogadro's number of them would contribute 1 R anyway. And there are 3 times Avogadro's number of them, so a total of 3 R altogether at most. Less than that, in fact, but at most. But there are already 3.5 Rs up here for the carbon dioxide, and there are a few modes, vibrational modes yet to add. They're probably pretty stiff. They probably don't add much, but they will add more than 0. And so we predict that the CO2 should be larger, the silver should be smaller. When we look it up, in fact, the silver has 25.4, the carbon dioxide has 37, so that prediction was indeed correct.